guys. We start the journey. We are getting towards the finish, which is good, right? Or not? I hope you are looking forward for the exam, because you let me see how good you are with computer arithmetic, don't you? But first of all, you will get a take-home exam. Okay, let us return to the division. Basically what we saw is the division, it's actually a matter of localization in a space. While in addition and multiplication we are essentially looking on an approach which can be applied regardless of what's going on, you know. Okay. Then for division, okay, there are particles which are tunneling in the system. Actually, they open the door. It's not tunnel. Then in division, we have a space which is determined by D and P, or by the divisor and the dividend. And essentially speaking, it's a convergency. And you are in this space, okay, which after the shift is large, then you want to return in a normalized space. And then you do moves in and out from this space, and depending on the radix, this can get larger, and then you have more choices to go back. Then, if you want to make a good divider, you have to understand a bit of geometry. You have to make a plot, which we call PD plot. It's a bit of incoherent in notation, because when we speak about this kind of diagrams, we have D and we have the shifted partial remainder, which we usually call S or Z. When we make the other type of plots, we have D and P. P and S or Z are kind of the same. Now, in this quest for the solution, you have two challenges. To find the location in the space where you are, and depending on that location, to determine the quotient, the digit, the next digit, and then to do the subtraction or the addition to perform the normalization. Now, this is a general diagram for radix whatever division. As you see, in order to diminish the redundancy level, you can do some scaling on operands. Then instead of going for the full dynamic range, you can do some scaling. And scaling, as we saw last time, has a plus and a minus. The plus is that I can get rid of some of the values which I don't like, you know, 5D, 7D, things like that. Or in our case, we started with radix 4 in -3 + 3, and we ended up in -2 + 2. Then I got rid of the formation of the minus or plus 3D, but the diagrams, you know, the space is getting more crowded. And this is making the decision a bit more difficult. Now, in that space, you know, you should see it in 4 quadrants. You have some separation lines, and the beauty of the entire scheme is the fact that you have overlap. In each region, you have 2 choices which are legitimate. And due to this freedom, you can now count on an evaluation of the partial remainder, not on the precise calculation. And as you see in here, due to the fact that you do an evaluation, your partial remainder is actually in this point, but it can be anywhere in this box, or anywhere in this box. Because you want to make separation between those regions, you actually should not allow such a box to span over 3 regions. Because if it spans over 3 regions, it will be no choice that will satisfy all of them. Then if you are here in this B, you can be here, you can be here, or you can be here. There is no choice in this box which will satisfy all of them. In this box, however, there is a choice which satisfies all of them due to the fact that here I have an overlap region. Now, it's a contradictory kind of requirement. From one point of view, I would like to inspect less bits of P, because P is stored in carry save format. Then if I inspect 4 bits of P, I'm actually inspecting 8 bits of P. From the other point of view, the more bits I inspect in P, you know, the wider is this box, and then the easier the embedding within the diagram. Then at the end of the day, what you want to do is you want to create a grid over your space. Then, again, you should think this as 4 quadrants. You have the separation lines, and you partition your space with a rectangular grid. Within each box in the grid, you should be able to assign a value for the quotient. Then if I am located in here, which means I am in this box, I am getting a value for the quotient. Now, there are, again, 2 things. From the point of view of the efficiency, I would like those boxes to be as large as possible. But from the other point of view, they cannot be larger. They cannot span over 3 regions. 2 regions are okay due to the overlap of choices. 3 regions will result in a non-valid calculation. And you see here as an example that this is a separation line, it's a staircase, and in this area you can actually choose beta or beta plus 1, doesn't matter which one you choose, will be fine. Now, the choice in that box will depend on the minimization and on the way you do the calculation. If this will allow you to simplify the calculation, you should put beta. If beta plus 1 is better, you put the other one. Now, the question is, how many bits do I need? I need a kind of estimation. Then when I draw the PD plot, I need to know how many bits should I inspect from P and how many bits should I inspect from B. This will be determined by some coordinates in my space. Then, let's say the minimum requirement resolution on P is the distance between those 2 lines. And because the lines are going in this way, the smallest distance is here, close to the minimum. And that one, delta P, will determine the minimum number of bits that I should inspect from P, which is, you know, the minimum amount that I should be able to detect. For B, the same story, is the smallest distance between 2 lines, but now on the horizontal part. Now, it's a bit of geometry. You get that kind of delta D and delta P, and that will tell you how many bits you actually need to inspect. In which way? You have here an example in which way. You know, you have an example. Then again, in order to do something for division which makes sense, I have to know my dynamic range and the digit set. I cannot go with this exercise without specifying this. Because if I don't specify that, it's very general and I cannot do any kind of calculation. Now I have a radix 4. This is, you know, it's a normalized range for D. As you will see later on, that when we deal with floating point numbers, this range is changing. In floating point numbers, there are between 1 and 2. That will be a bit later. Now, based on that, you do the calculation, and essentially you obtain that delta B, delta D is 1 over 8, and delta B is this, which means, oh, good morning, but I saw you before. Are you a ghost? Okay, now, based on these values, you actually determine that you need to inspect at least 3 bits. And because of the fact that you keep P in carry save format for P, you need to inspect 4 bits per element. Now, this is a beautiful theorem, which I don't want you to prove or to understand how it's proved, but this is telling you the following. Then if you do that calculation for your diagram, in practice what you will need will be 1 more bit. Okay, these are more like, you know, cookbooks. You don't need to prove that theorem. You just have to have in mind that kind of things. Okay, there is an upper bound. Okay, now there are some other tricks and warnings. The first one, it's about the non-symmetry of the selection. Because you do business in 2's complement, symmetric points do not get the same kind of, then you might expect that because B is symmetric with A, that you would have here minus B minus 1. Actually, it's not true due to the 2's complement representation. There is symmetry in this diagram, you can rely on it, but you have to be careful because sometimes it doesn't hold true. The other one, which is usually utilized in practice, is to allow for exceptions. That you see in this example, I could make the boxes small as this one, and then I have no problem. But what I want to diminish the complexity of my logic. Then I would like to inspect less bits of P. And this will be possible. I can increase, you know, the dimension of the box. And everything will be fine except for this one. Because this box is now covering 1, 2, and here a bit of the 3rd region. Then, according to the rasterization of the space, this is not a good choice. However, I can mark that area as an exception. Then, when I am here, I will not get the quotient directly, but I will do a further analysis to see exactly where I am. If I am here in this part, or let's say in a part, somehow I will make now a refinement on the selection. Then I will analyze this at the lower level, let's say with 4 of those small boxes. And this will help me to do things most of the time less complex, and whenever I have a problem, I will treat it as an exception. Now, this is a complete PD plot. This is for a radix 4, minus 2, 2, and in here you see that you have exceptions in this area, and what you see in red is actually the reason for the famous Pentium bar. Maybe you heard about that? Were you active in the field in that time, or you were kids? I don't remember when was the Pentium bar. Okay. Then, as you see, the design process is kind of automatic. I am writing a C program which is generating a PD plot. In the PD plot, I'm embedding the staircases, then I am assigning to each box a value, and then I'm generating a lookup table. In the script which was doing that, it was a bug, which created troubles in that kind of situations, which were not very often, and that's the story of the Pentium bar, which created a lot of waves in that time, but now it's history. Okay. Now, what we saw is that division, it's a convergence process, that by its nature, it's serial. We can rely on high radix, but high radix is complicated, the digit selection, and then we moved our problem into geometry. We make a drawing, we have a space, we do some kind of partition of the space, and then we have the decision for the quotient based on a kind of partition of this area. There are also other things that we can do, let's say, to improve division, or let's say to alleviate some of the issues, because there is no panacea universalis. You have to pay here, you get there, and one of the direction of doing that, it's pre-scaling. If you look at the division diagram, okay, what you see is that close to the minimum value, the lines are closer, and when I get towards the maximum value, the lines are, you know, more far away. Now, somebody came with a brilliant idea and said the decision in the general case, it's actually determined by the closest line here. What if I move always my problem in the neighborhood of the maximum value? Then if I do some kind of pre-processing, and regardless of the values that I'm taking as operands, I will move my decision in this area of the space, I'll have more room for decision. And this is pre-scaling. Then, what you do is, regardless of the value, you multiply with something, and then you get around the max. And now your space, it's always here. You cannot be here. You are always in the neighborhood of the max. Now, because you are now in the neighborhood of the max, the partition of the space in this area, it's almost always, or if you do a good job, it's only based on horizontal lines, which means you should not inspect any bit of D, and you will inspect not very many bits of P. Then the effort to determine the digit, it's actually a lot lower. What you have to do is you have to invest in the pre-processing and to do that kind of scaling from wherever you are in this area. This will cost you some kind of multiplications, but the idea is to choose that values for multiplication in such a way that you don't do multiplication. And in here you have some examples on how you do that. Let's say you have unsigned division between 0.5 and 1, and then you partition this in different domains, and for each domain you actually do some kind of multiplication, then which are shifts and adds. Now the domains, I choose them in such a way that I don't have to make a comparison. I'm just inspecting some bits from D. Then I'm not comparing D with a number. It's not an addition. It's just inspecting some bits. You know, if it starts like that, I have this. Now, you see, depending on where I am, I will do a shift or a shift and add. And then I will be in this area, then I will be in the neighborhood of 1, always. And then if I start in the neighborhood of 1, I'll always stay there in the convergence process. Now there are some implementations where they use the multiplier, actually the partial product part of the multiplier in order to do that. Now, quite sure that if you change the dynamic range, this will change. And you spend one cycle to do this, but you will win later on, because later on the decision process is a lot simpler. Okay, this is another technique, and this is essentially anticipating computation. Do you remember carry select? In carry select, we are doing the following. We are partitioning the operands in 2. Let's make it simple. And then for the least significant part, we are doing addition. And for the most significant part, we are doing addition for the two cases, when a carry was coming or no carry was coming. When I'm done with the first part, I do a select. The story is exactly in here. What is happening is I'm doing a radix 2 division, but I am producing like a radix 4 division, because I am busy now with inspecting this to determine the current digit. However, in the same time, I'm looking for the next digit, and I'm trying to compute what will be now the outcome of the next iteration in a speculative mode. Then I'm subtracting d, I'm adding d, and I'm doing nothing. In both cases, I am determining the quotient digit, you know, the next iteration. And when I am done with this calculation, I can select this one, and I can complete another one. Then in one iteration, I am actually producing two quotient digits. One in a normal way, the other one in a speculative way. This will cost me more hardware. Then it is kind of radix 4 division. It may be faster or slower than radix 4 division, depending on the implementation. But the principle, it's a beautiful principle of computer architecture in general, to do speculative execution, speculative calculation. And this is exactly what you do here. I'm not sure whether or not this was implemented in practice. But as a solution, it's kind of, you know, it's an elegant solution. Does it sound familiar? The image, right? It looks like an array multiplier, but it's not. It's an array divider. It is working in the very traditional way of division. What I'm doing, this is a restoring array. And what I'm doing, I'm making the first subtraction. The first subtraction will produce me the first bit in the quotient, which now, via this max, will select to pass the result in the next, or to do restoring. In the next level, I'll do the same. Then practically, I have a structure which is very much similar with multiplication. But now, each stage is controlled by the previous one. Then I am doing the first, it's like the first subtraction, I use the result to select if I'm restoring or not. And the other advantages are there. I have broadcasting lines, I have very regular thing, but there is a fundamental difference between the array multiplier and the array divider. As you see, now the critical path is really, really long. Then I have to do meandering, you know, I'm like a river, like Seine. You know, have you been to Paris? The Seine is doing meandering in Paris, right? If you didn't go to Paris, you should. It's a nice city. Okay. Now, you can already guess why such a structure is nice. I can use it as multiplier, as divider. I can also pipeline it, but things are getting a bit more complicated than they used to be for multiplication. Okay. Actually, this idea is not really working because you are damaging the beauty of the scheme. Okay. Forget modular dividers and reducers. This is an important part in arithmetic, Montgomery reduction, but is not enough explained in the book, and in order to cover it enough, we have to spend more time. This is essential for cryptography. And this is the solution is beautiful, it's interesting, and if you will ever do things with cryptography, just remember the Montgomery reduction. Okay. The guy, I think he's still working for Microsoft. Montgomery. He came with an interesting idea, but it's essentially his approach is based on some mathematical manipulation, and then the implication in engineering are nice. Remember that for multiplication we had a particular case which was called squaring. When the two inputs were the same, you could simplify the multiplier and you obtain the squaring. You could also think in the same way that you could try to do square root with the same kind of structure, right? But this will not function because while in the previous case you knew the input operands, in order to use a similar simplification you need to know the square root, which you don't know. However, you may think this might be easy. Then this is, I'm computing the reciprocal. Then it's 1 over x or 1 over y. And because z is always 1, I should get a simplified kind of approach. This is not really true, unfortunately. There is a method to do that, which again is not well explained in the book, and I will just mention a bit on it, which is this one. What this method is trying to do is to speculate on the fact that z is 1. Instead of having normal iterations, you have two iterations which are coupled, and then you have, how should I put it? You have a low accuracy iteration and a high accuracy iteration. They work in parallel, and they will allow you to complete the calculation in less time. But you will have to have two engines, each of them implementing, again, a different kind of convergence rule. Then Montgomery and this one, don't bother, okay? Then I will not ask you at the exam about those. If I do, you can protest, but I won't, I'm pretty sure about that. They are not explained enough in the book. It's kind of too shallow, and also it's not essentially relevant. Now, as I kind of mentioned, the array multiplier and also array divider, and on the serial multiplier and serial divider, you see there is similarity between the two, and this can help you to share the logic and to do combine, multiply, divide units. Then you will have the same logic, and you will have a controller. Depending on this controller, depending on the nature of the instruction that you are executing, this controller will tell the logic what to do. This can be advantageous in some cases because your application might not use division, for example. Now, I may have a lot of multiplications, and then I may have one or two, I don't know, fast 3 multipliers, but I can also have that kind of slow hardware, which I can use for multiplication, and I can get some advantage in a processor architecture. And whenever I need to do a division, I can rely on that. And the same holds true for these guys. You see again, they are very similar. Doesn't matter that this one is laid out like that, right? We can always make it. And this is usually the layout in a processor. And you have it like a box and you use it one way or another. Okay. Then I could also say that we finished the division, and I could say the division is a convergency process. And as I said, we ended up by playing with a bit of geometry, and we have a space and we draw lines and separation stuff. But we can also go further and try to speed up division, and to try to see if there are kind of different ways to do this better, right? Then in what we know, we are converging to the quotient starting from an initial approximation in steps. And this is a restoring kind of convergence. The performance is determined by the number of steps in the convergency, but also by the power of the operation that I'm doing. And we are relying on addition. Now the question is, can I rely on a more powerful operation and do division? Like instead of addition to use multiplication. Assuming that multiplication is a more powerful operation. That's one question. And the second question will be, what will happen if I'm doing such an approach? Will I still have that kind of linear convergency? Because in here, I need as many iterations as bits or digits in the quotient, plus 1 or 2, depending on what I do before and after. If I rely on multiplication, can I get less iterations? And if I can get less iterations, then it will be quite okay. Why is that? Multiplication is more expensive in hardware, but it's not a lot slower. And if I diminish the number of steps in the iteration, I can win. And that's the principle behind what we do here, okay? Now, this is a more general approach of solving things by convergence. Then I have a couple of functions, and those functions, I compute them in an iterative way. Let's say I have the function, the first function, which is u, which I will do some kind of calculations, then each and every iteration I'm computing the new value based on the current value of it and of the other one, and I will make this converge to a constant. I have the other function, which is my target function, which I also compute in an iterative way based on the previous values of the two functions, and that one will converge to whatever I want. And I can have not one, I can have more. Then I can do by this trick the evaluation of more functions. Now, in here, those are the two parts, right? The rate of convergency, then linear or quadratic or whatever, and the difficulty to evaluate the functions f and g. In the normal division, our function was an addition. It's not difficult. Let us see if I can make more complication in the function and get better kind of convergence. And I think the first one is division by repeated multiplications. Then I am computing Q. And what I want is to multiply Z and D in an iterative way with some products in such a way that D multiplied with X whatever will go to 1, which means that Z multiplied with X whatever will give me Q. The error will be determined by the error of this evaluation. This will not be able to give me precisely 1. It will be 1 minus unit in last position. The more iterations I do, the closer to 1 I get. Now, this is a very different way of looking at division. Then I'm not doing addition, decide, whatever. I'm just multiplying. I have to see how I select these terms, xi, I have to know how many iterations, and I have to know how to implement that in hardware. As you see, this method is not giving me the reminder. Then I'm just producing the quotient. If I need a reminder, I will have to do a multiplication and an addition. Then convergence methods provide you just the quotient. Now, this will not be true in all cases. I mean, I can do that assuming some kind of dynamic range for my operands. Otherwise, this will not function. But as I said many times, if I'm not in the dynamic range, I will do whatever is required to get there. Then I solve the problem in the dynamic range and I return where I want to be. Okay. Now, this is a choice for the multiplier xi, 2 minus di. Then, remember d, it's unknown. It's a fractional number. It's again normalized between 0.5 and 1. Then if I choose those, then at each and every iteration, I will have to do 2 multiplications, essentially. 2 minus di, it's actually for free. I will solve that problem, you know, when I'm doing the multiplication. I just have to do a complementation, and that's it. Then each and every iteration, I'm multiplying the previous value with 2 minus the previous value, and of d and z with this. Now I start with d and z, and because this will converge to 1, this will converge to the quotient. Now, the choice for the products that I'm using for multiplication is done in such a way that I get convergency, and I also am not making my life more complicated than it should, because I can also make different choices, but this will make those complex. What I see now is that in each and every iteration I'm doing 2 multiplications, but they are decoupled. There is no dependency. Then each cycle will basically take 1 multiplication plus a bit of an overhead. Okay. Then, how fast do I converge to the solution? To see that, I have to play a bit of mathematics. Then I know that d will converge to 1, and it will get close to 1, but it will never be 1. Now, assuming that I have the calculation of the dth iteration I plus 1, which is this. If I do here the multiplications, what I will obtain is 1 minus di squared. Then this is the error at iteration I plus 1, and this is the error at iteration I. Then I see that the error at the next iteration is actually quadratic. Then while in the addition case I was having linear convergency, then now it's quadratic. Each iteration, the error, it's actually getting a lot lower. Which means that now, in order to arrive to the solution, I do not need k iterations, but I will need logarithm of k. Now, this is beautiful from one point of view, but now if I really want to see what I get, I have to see how much time it will take me to complete a multiplication. If the multiplication is fast, then I will have a fast result. If the multiplication is slow, I may end up in not having such a beautiful result. But it is important that I have quadratic convergency. If the convergency would have been linear, then forget about the method. The method would not be good. Now in here, you see the process of quadratic convergence. Then you start, in each and every iteration, you clarify a number of bits. Then this is an iteration 0, and you see you have only one bit, which is clear. The next iteration you double, you double, you double, you double, and then in here you have 1 minus unit in last position. You cannot go more than that. Now this is giving you a hint. The first iterations are not very effective because I'm not winning a lot, while the difference between, let's say, this iteration and this iteration is large. Then the method is like a car, you know, you have to get the speed, and at the beginning it's kind of difficult to start. Now, this is a hint that you can apply the method. What do you see in the cup? It's like a kaleidoscope. Do you see me in colors and moving like that? Then this can give me a hint that if I can find a way to avoid the first iterations, then instead of doing them just to make a lookup in a table and start with an approximation, which is, let's say, 4-bit valid, I will just need 2 more iterations because I'm very effective. This is me going towards 1. But remember, this is not my goal. My goal is to get the value of q. But the faster I get towards 1 with this one, the faster I obtain the q. Okay. Okay, then this is the convergency. We discussed about that. That's another method. This is Newton-Raphson. You heard about Newton-Raphson. Don't say you did not, because I don't trust you. Okay, now Newton-Raphson can be utilized to do more than division. You can actually use it to compute the root of a function in general, in an iterative way. Then you have a certain function, and you compute the root of the function. It's not the square root. And for Dutch-speaking people, it's not the wortel, right? Because I heard that kind of confusion. Then one is square root, and this is root. And this is the value for which the function is 0. And you can use an iterative method based on this kind of tangent to get from this approximation closer to this point, which is the root. Now, in order to do that, there are 2 things. First of all, you have to make a choice for a function. You have to find a function which is giving you whatever you are looking for. And in that function, you have to have involved your parameters. Second, you have to determine the iteration, the calculation. Again, this is now based on the previous value and some kind of evaluation. In here, you need to compute the derivative of the function and do some things. But this is just the theoretical equation. In practice, what you will have to do as designer is to make a choice for a function which has as root the value that you are looking for. And then there is more than one function which gives you that. Then you have to find the one which is simplifying that expression. And also, when you obtain the expression by means of algebraic manipulations, you should try to make it in such a way that from the point of view of the implementation in hardware, it's more effective. Then work a bit around the expression in order to get something which will not cost extra calculations at runtime. It will cost you a bit more effort with pen and paper, but it will be more effective in hardware. Okay, you can get a break and speak after.